Hello there. In this video, we will discuss about direction cosines and direction ratios at first. For direction cosine, let us take coordinate axes x, y, and z. Let OP be any line which makes an angle alpha with the positive x-axis. Just be careful, positive x-axis, and it makes an angle beta with positive y-axis, and this line makes an angle gamma with positive z-axis. So here we can say this alpha, beta, and gamma are the angles made by OP with positive x, y, and z axis. Alright, so these angles alpha, beta, and gamma, they are known as direction. These are known as direction angles of the line OP. Okay, so these angles alpha, beta, and gamma, which is made by the line OP with positive x, y, and z axis, are called direction angles, and cosines of these direction angles, which is cos alpha, cos beta, and cos gamma, they are called direction cosines of the line OP. So this cos alpha, cos beta, and cos gamma, they are called the direction cosines of the line OP. This OP, and these direction cosines are also denoted as L, M, and N. These are also the direction cosines of the line OP. So what we made a conclusion is that is L equals to cos alpha, M equals to cos beta, and N equals to cos gamma. So we can say that the cosines of the angles which a straight line makes with the positive direction of axes of coordinates are called direction cosines of a line. Here alpha, beta, gamma, these are the angles which a straight line makes with the positive direction of x, y, and z axis. So cosines of these angles, cosines of alpha, beta, and gamma, they are called the direction cosines of the line OP, which is also denoted by L, M, N. So whenever we say L, M, N, you always remember these are the direction cosines of a line segment. Now let P, X, Y, Z are the coordinates of P, and let OP equals to, here let us consider OP equals to R. The length of OP is R. Now let us draw a perpendicular from point P on Y axis. So I have already discussed what is the angle made by OP with Y axis. Yes, it's beta, isn't it? Now whenever we draw the perpendicular, let us say this point as R. Okay, so in this right angled triangle, this POR, what is cos beta equals to what? Curly brown here. So it's OR upon OP. So OR, cos beta is cos beta here. OR, O to R, it's y axis. So from here to here, it's y coordinate. So it's y, isn't it? And OP is given as R units. So in place of OR, I can write y upon R. Is it? So therefore, y equals to what I get? R cos beta. In similar way, what I can get here is, similarly I can get x equals to R cos, with x axis it makes alpha angle alpha. Similarly z equals to, I can get R cos gamma, isn't it? So I have got three results over here, where this we can write also we can write like this: R equals to x upon cos alpha, is it? And R equals to z upon cos gamma, and also R equals to y upon cos beta also. We can write like this also. So if we square and add this, what we get is x square plus y square plus z square. We can easily get R square is common, cos square alpha plus cos square beta plus cos square gamma, isn't it? So x square plus y square plus z square. So if P, x, y, z are the coordinates of OP, then simply this means R square. So here R square cos square alpha plus cos square beta plus cos square gamma. So R square cancel out. It's 1 times. So therefore cos square alpha plus cos square beta plus cos square gamma equals to 1. But but cos alpha represents L, cos beta represents M, and cos gamma represents L. So this can be written as L square plus M square plus N square equals to 1, which is the important result here in direction cosine. Again, see here, cos alpha represents L, so x equals to, we can write here RL. Cos gamma represents N, so we can write here Rn, and cos beta represents M, so we can write here Rm. So if x, y, z is the coordinate of the point P, then in place of x we can write RL, in place of y we can write Rm, and in case of z we can write Rn. So the coordinates of P can also be written as RL plus RL, Rm, and Rn respectively. So here we can make another conclusion that x equals to LR, y equals to MR, and z equals to NR. So this relation is also important, or this can be further written as L equals to x upon R, M equals to y upon R, and z equals to N equals to z upon R. So this relation is very much important for further purpose. Now let us discuss about the direction cosines of x-axis, y-axis, and z-axis. Since x-axis makes an angle 0 degree with itself, 90 degree with y-axis, 90 degree with y-axis, and 90 degree with z-axis, and 90 degree with z-axis. So these are the alpha, beta, and gamma of x-axis, isn't it? So cosine of this angle, cos 0 degree, cos 90 degree, and cos 90 degree. These are the direction cosines of x-axis, which is equals to cos 0 means 1, cos 90 means 0, and cos 90 means 0. So the direction cosines of x-axis are 1, 0, and 0. Similarly, we can get the direction cosines of y-axis and z-axis. You can say it. So just say, what are the direction cosines of y-axis? Yes, it's 0, 1, 0, and that of z-axis? Yes, it's 0, 0, and 1 respectively. So take a screenshot if needed. Now let us discuss about direction ratios. Let PQ be a line whose direction cosines are given. So DCs of this line is L, M, N, it's given. Let us suppose it's given. So if L, M, N are the direction cosines of the line PQ, then the three non-zero numbers A, B, and C, these are the direction ratios of this line PQ. If L, M, N are the direction cosines of PQ, if and only if the direction cosines L, M, N, and the direction ratios A, B, C, they are proportional. So what we can say is that these three numbers, non-zero numbers A, B, C, are said to be the direction ratios of the line PQ if L, M, N are the direction cosines and L, M, N and A, B, C are proportional. So here is the definition of direction ratios of a line. Any three non-zero numbers A, B, C are said to be the direction ratios DRs of a line with direction cosines L, M, N if A, B, C and L, M, N are proportional. That is, L upon A equals to M upon B equals to N upon C equals to plus minus under root. So this one, you understand this. So as before, I have proved L square plus M square plus N square equals to 1, isn't it? So it's 1. Under root of 1 is 1, and it is this is as it is. So equating these individual first and last, second and last, and third and last ratio, we get L equals to this, M equals to this, and N equals to this. So here, if positive sign gives the direction ratio of line AB, the negative sign gives the direction ratio of line BA. And don't forget that DCs are unique for a line if they are parallel also. But direction ratios of a line are not unique. L square plus M square plus N square equals to 1. But it is not necessary that A square plus B square plus C square is always 1. It might not be 1. If it is 1, then it's fine. It's unfortunately. So now let's discuss how to find out the direction cosines and direction ratios of a line segment when its coordinates of endpoints are given. So here PQ is a given line segment. So first of all, let us find the distance of PQ by using distance formula like this. So let us consider this as R. So direction cosines of the line PQ is represented by element. So direction cosines are always represented by element, whereas direction ratios of a line are always generated by ABC. So first of all, let us go with direction ratio. So direction ratio of this line PQ is given as ABC equals to x2 minus x1, y2 minus y1, and z2 minus z1, where A equals to x2 minus x1, B equals to y2 minus y1, and C equals to z2 minus z1. So here this this relation can be written as under root a square plus b square plus c square, because a, b, c represents x2 minus x1, y2 minus y1, and z2 minus z1. So similarly, direction cosine of this line PQ can be calculated by, is denoted by element, and we can calculate this by x2 minus x1 upon r. That means this x2 minus x1 is the direction ratio, isn't it? And r is the length of PQ, where r is the length of PQ. So if we subtract the final coordinate with the initial coordinate and divide by the length of that line segment, then we can get the direction cosine also, isn't it? So similarly, y2 minus y1 upon r and z2 minus z1 upon r. So a upon r, b upon r, c upon r. Why? A represents x2 minus x1, b represents y2 minus y1, and c represents z2 minus z1. Also, this r can be written as under root a square plus b square plus c square. So here, in place of r, we can also write this one, m equals to this and n equals to this. Now let us discuss about the condition of perpendicularity and parallelism of when the direction ratios and direction cosines of a line are given. So let us discuss about two lines. Let AB and CD are two given lines, and if their direction cosines are known, then angle between AB and CD is given as cos theta equals to n1 n2 plus m1 m2 plus n1 n2. And if direction cosines of any two lines are known, then angle between that two lines can be calculated by using this formula. Now, condition of perpendicularity, if the direction cosines are given, then we can use this, because cos theta, cos 90 equals to 0. So simply making these terms equals to 0. And condition of parallelism, you just remember this one. And don't forget that direction cosines of any line segment which are parallel, they are unique. That's why L1 equals to L2, M1 equals to M2, and Nn equals to N2. There is a proof of this as well, but that's not necessary for you. Only this relation is important. And similarly, if direction cosines are given, direction ratios are given, then we can, the condition of perpendicularity is a1 a2 plus b1 b2 plus c1 c2 equals to 0, because cos 90 is 0 and this denominator becomes 0. So finally this numerator equals to 0 is the condition of perpendicularity. And whenever direction ratios of any two lines are given, then the condition of parallelism is a1 upon a2, b1 upon b2, c1 upon c2. Okay, you can have a screenshot if you needed it.